Okay, so
Sounds good. Let's go. Yeah, but how do you
okay, so this helix looks like this. You have a coordinate system.
just take one over?
It's hard for me to think while you're talking. So you have let's say z. Let's do it like this. So x, y, z. And can I draw this? It's going something like that. Okay. What we are given is the path parameterized by z. So it says this is the path z, cosine of 10z, sine of 10z. No, these must be switched. Okay. And the speed is constant at 0.2 meters per second.
The Z was in the Z spot, and the other two are shifted out, aren't they?
Yes. I thought that's what I just changed. Yeah. Okay, so we're trying to come up with, oh, and is it going up or down? Remember, you have to think about whether the thing is moving in the direction on this parameterization of increasing parameter or decreasing parameter. Our parameter is z, so the question is this thing moving up this helix or down this helix? If it's moving up, then you're just going to take the derivative with respect to z. If it's moving down, you're going to have to multiply by -1. Anybody have any questions about that? Are you with me on that?
Is that something provided or?
That's something that's always true in these kind of problems. So if you have a parameterization, so for a path that's parameterized by, I'm just making up some variable s, then, and let me give this a name, let me call it P. Then dp ds is tangent to the path in the direction of increasing s, and negative dp ds then is tangent to the path in the direction of decreasing s. Okay, s is just a stand-in for whatever your variable is. So instead of s, we have z in this problem. So if we take dh dz, it's going to give us a vector tangent to this path moving in the direction of increasing z, so tangent to the path, but for a particle on the way up this helix. And if we take negative dh dz, it'll give us something tangent to the path, but moving down the helix. Okay, so the particle's moving upwards, so we just want So a vector in the direction of motion, tangent to the path, as a function of z, is just going to be dh dz. And so that's going to be 1, no, I keep doing that. I'm so used to x being the parameter. Okay, negative sine of z, positive cosine of z.
10z.
Yeah. And then 1. Okay. And then we're trying to come up with a velocity vector as a function of z. So what I need is to make this a unit vector and then multiply it by that speed. So the length of this vector, the magnitude of it, is this thing squared plus this thing squared plus this thing squared, all square root. And so this is 100 sine squared of 10z plus 100 cosine squared of 10z. Well, notice that 100 sine squared of 10z plus 100 cosine squared of 10z is equal to 100. And so the magnitude of this is 101, square root of 101. Okay, so in other words, the unit vector in the direction of motion is this thing divided by square root of 101. So negative 10 over root 101 times the sine of 10z, and then positive 10 over root 101 times the cosine of 10z, and then 1 over root 101. So there's the unit vector. And now we just have to multiply that by the speed to get the velocity vector. The velocity vector is a function of z. Is 0.1, so this comes out to be negative 0.199 sine of 10z, positive 0.199 cosine of 10z, and .0199. Okay, so that's the velocity vector. And then once you're there, you've gotten to the point where this is just like every other problem. The acceleration is going to be dv dz times dz dt. And dz dt is this. So you get negative 1.99 cosine of 10z, positive 1.9, no, negative 1.99 sine of 10z, and then 0. Uh, 1.9, and then I'm multiplying that by 0.0199. So I guess I might as well calculate this. So negative 0.0396 cosine of 10z, negative 0.0396 sine of 10z, 0.
Thank you.
Yeah, sure. Any questions about that? Did I do the thing again that I did in the solution?
Yeah.
Okay.
Oh, it was the cosine part.
Oh,
where you get the,
Oh, yeah, the trig identity.
Yeah.
Yeah.
That's the part I was thinking.
Okay, yeah, anytime you see a sine and a cosine, if those have the same argument, they add up to 1, remember that?
Because in your solution, you went straight to the velocity vector.
Okay,
So
okay,
I was a little confused how that
Yeah.
came about. Okay.
I was probably so tired of doing solutions. Any other homework questions? Okay. So last time we were talking about circular motion. I want to talk about relative motion and get that done today because circular motion and relative motion are going to go together so well, so often in this class. And as we go through relative motion, I want you to think about these, let's say, 3 things. Okay, first of all, when I talk about different coordinate systems, always imagine a coordinate system being a video camera. Except it's some kind of funny video camera that can see all the way around, you know. But it's something where you can take measurements from it. You can tell how far the object is this way, how far it is this way. Okay. So think of a coordinate system as a video camera. With coordinate axes mounted to it. Second, remember that there are 2 ways to make it so you can't use Newton's laws from a coordinate system. So that means 2 ways to make a coordinate system non-inertial. Okay, inertial coordinate systems are what you need for Newton's laws. So this is 2 ways to wreck a coordinate system if you're trying to do Newton's laws. Okay, the first one is the origin of the coordinate system is accelerating. And the second one is the coordinate system is rotating. In this section, we're going to see these. But this whole, like the overall topic here is particle kinematics in a non-rotating coordinate system. So we're still not going to have these. Until later. Much later.
Stupid question.
Yeah.
I'm just trying to understand what you mean by one. When you say coordinate axis mounted on it, do you mean printed on the lens?
Yeah, think of it like that. That's a perfect way to think about it. Or you could, since it's 3-dimensional, yeah, from 2 axes. So yes, if you know the x and y directions, that defines what the z direction has to be. So yes, imagine an x and y on the lens. And so that just determines the orientation of the coordinate system.
Got it.
Yep.
As opposed to project.
As opposed to you have the camera, you take the measurement, and then you decide whatever coordinate system you want afterwards. It's defined for you. Okay, and then the third thing is whenever we have 2 different coordinate systems, their orientations are going to be the same. Okay, so right now we're not worried about one coordinate system with the z-axis up talking to another coordinate system with the z-axis horizontal or whatever, okay? They're always the same orientation. So that just simplifies the math a little bit. Okay, so these cameras, one could be accelerating, one could be at rest compared to us. One could be accelerating anywhere it wants, but the whole time it's accelerating, those orientations are staying the same. Okay? You with me on that? Okay, so now let's say that first think of position vectors of an object, some defined object. And that object, I'm going to call P for position. In 2 coordinate systems, A and B. Okay, so here is the coordinate system A. Here is the coordinate system B. And remember that the orientations have to be the same. And then here is the object P. Okay. And maybe the most confusing thing about this, honestly, is the notation. So what do the position vectors look like in these coordinate systems? Well, from the video camera at A, coordinate system A, that's the position vector, right? From coordinate system B, that's the position vector. And now here's the naming convention for these. This is the position of P observed by A relative to A. And so that's the notation. Position of P relative to A. Okay? And now that means that this one is the position of P relative to B. And just like we can do this, we could think of figuring out A can also see the origin of B, right? So you can think of a position vector of B that's observed by A. So what would this be called? Position.
B over A.
Yep, exactly. B relative to A. And all that stuff, I mean, if you accept that naming convention, that stuff is all clear. So what's the relationship between these things? I mean, just think of how vector addition works. The position of P relative to A this vector here has to be equal to this plus this, right? So I'm going to write that as the position of P relative to B. I'm sort of doing it in the opposite order you would think, but plus the position of B relative to A. So this is always true for any two coordinate systems, and here's the way to remember this. So this is like a memory device. Think of those as fractions, and think of it as fraction multiplication. So the subscripts for this to be correct have to work as fraction multiplication. So P over A is equal to P over B times B over A. One thing that's sometimes helpful is if you have anything, I guess I'll make up two new subscripts, but let's say if you have a position of M relative to N, that's always the opposite of the position of N relative to M.
And that was my question, so like you could look at this the other way around, like the.
Yeah, you just have to, thinking of it the other way around makes you paranoid because you think everything's a video camera. But yeah, exactly, like if it makes more sense if you just think of A and B, you know.
But P, A over B is also valid.
Yeah, all those are real things, yes. So, right, if you wanted to know what position of A relative to B was, well, it's just going to be the vector that way. So it's going to be the exact opposite vector, and you switch the subscripts. Okay. This is going to be true with positions. It's also going to be true with velocities and accelerations, which is the next thing I'm going to bring up. So velocity of M relative to N is equal to negative velocity of N relative to M an acceleration of m relative to n is negative acceleration of n relative to m. So for all of these, if you switch the subscripts, you switch the signs. Okay, so now how do you get velocity and acceleration relationships? Now you can just take time derivatives. Derivatives of the position relative motion equation. If you take time derivatives of both sides of this, you just get the velocity of p relative to a is equal to the velocity of p relative to b plus the velocity of b relative to a. And again, all of these have to work as fraction multiplication if you have it set up right. And now take another time derivative and you get that the acceleration of p relative to a is equal to the acceleration of p relative to b plus the acceleration of b relative to a.
Did you scroll up half a line?
Yeah. Okay, so I think that's the math of it, but really it starts to make sense once you start to use it in a lot of example problems. So let's start doing a few example problems. Here's the first one. It's sort of, it's kind of a simple case, but let's say that a person on an elevator drops their keys. Oh, I'm still thinking about that lady. It doesn't go in the slot though. Person on an elevator drops keys while the elevator, during that brief period where it's accelerating up. Okay. Okay, a camera on the elevator measures the acceleration of the keys as 11.5 meters per second squared down. The question is, what's the acceleration of the elevator? Okay. Well, let's choose a coordinate system. We can just do this in XY coordinates. So let's think of X as horizontal, Y is up. And what do we know? We know the acceleration of the keys relative to the ground. If it wasn't a camera fixed to the elevator watching this, but it was a camera fixed to the ground and everything was glass or whatever, we know that this acceleration would be 0, negative 9.81. Okay. We know that the acceleration of the keys relative to the elevator is 0, negative 11.5. That's what we're given. And what we want is the acceleration of the elevator relative to the ground. So we can set this up as the acceleration of the keys relative to the ground is equal to the acceleration of the keys relative to the elevator plus the acceleration of the elevator relative to the ground. Do the check, make sure that that fraction multiplication would work. You can see the e's would cancel out and it works. So this is the correct relative motion equation.
So you're like getting rid of the motion of the object.
Yeah, we're using two relationships we know to calculate a third relationship that we want.
And does this imply that our second coordinate system with the ground is not moving?
Correct. That's right. Yeah, that's the idea of this. Because that's how we know what the acceleration of the keys relative to the ground is. And the answer would be the same, just this is kind of a nitpicky point, but the answer would be the same even if it's moving on the ground, as long as it's moving with a constant velocity.
Yeah.
We just know it's not accelerating relative to the ground. Yes?
Subscripts fit where?
How I know what?
Which subscripts fit?
Oh, yeah. Into the equation or into the equation, yeah. Any set of subscripts works if it works as fraction multiplication. So as long as this is true, then it works as a relative motion equation. So what else could we, like we could have also done it as acceleration of the elevator relative to the ground is equal to the acceleration of the elevator relative to the keys plus the acceleration of the keys relative to the ground. That's kind of a crazy way to think of it, but you can still, now you know that this is equal to negative acceleration of keys relative to the elevator. The other two make sense. And so as long as that fraction multiplication works, it works. Yep. And so that's another thing you can do is just put them in any order. Don't even think about the problem. Put them in any order and then just do the switching subscript, switching signs thing to make them match. And that always works for problems. Okay. Okay, so now we have 0, negative 9.81 is equal to 0, negative 11.5 plus the thing we're trying to calculate. Subtract this one from both sides, and you get, so 0, negative 9.81 minus 0, negative 11.5 is equal to A elevator relative to ground. This is the same thing as just adding that 11.5, so we get that the acceleration of the elevator relative to the ground is 0, positive 1.69.
A lot of work trying to get.
Yeah. Yeah. I laugh because it's so painful.
It's that easy.
Yeah, right.
And somehow you're right.
Yeah. If you get those subscripts to work with the fraction thing, it's pretty foolproof, you know? Okay, so now the real reason that relative motion is going to be so important to us is, okay, so this is the key, no pun intended, application for us. Linkages. Okay, so here's what we're going to do. Here's a wall, and connected to the wall by like a hinge is an arm, and connected to that arm by another hinge is, let's say this one's horizontal. Okay, and to make the math sort of simplish, let's call this 1 meter, and let's call this 1 meter. And let's say that the arm connected to the wall has an angular velocity of 10 radians per second. And an angular acceleration of 5 radians per second squared. And let's say that the second body has an angular velocity the opposite way of 8 radians per second, and an angular acceleration opposite the angular velocity of 20 radians per second squared. And that point P is at the end of the second body. What's the acceleration of that point P?
And it's moving like a trebuchet.
Yeah, right. It's whipping around. And so it's sort of a chaotic scene, you know? But the way we're going to do it is we're going to think of this as one coordinate system, the ground coordinate system. We're going to think of this as another coordinate system. Okay, this point is just in circular motion around this. And despite the fact that this is moving, forget about that for a second. If this was a video camera, it wouldn't know it was moving. All it knows is that this point is moving in circular motion around it. Okay? So I'm gonna call this, I'll call this G for ground. I'll call this A, you know? We're gonna use circular motion to calculate the acceleration of A relative to ground. Okay? We're gonna use circular motion to calculate the acceleration of P relative to A. Then we're going to use the relative motion equations and get the combined acceleration of En. Yes?
So for the equations we just used, can we just substitute an angular velocity and acceleration for velocity and acceleration in those equations? Does it still work?
We don't have to do that. We No, that does not work. Because remember, we're not talking about coordinate systems rotating, only moving.
Right.
So later, when we do start having coordinate systems rotating, we'll have more problems than that, actually. But we'll get to that later.
Okay.
But for now, those aren't rotating, so we don't have to worry about stuff like that. Okay, so I'm gonna name these, so I'll call this G, is that hinge. This is A. And let's first calculate the acceleration of A relative to G. Let me write down sort of what I said here. So A is in circular motion around that pin G. And P is in circular motion around A. Okay, so first, acceleration of A relative to G. Oh, I didn't give this angle. This is 30 degrees. This is getting kind of messy, but this angle is 30 degrees. Okay, so how do you calculate the acceleration in circular motion? That's the watermelon equation. So all ripe watermelons will rot. And now we just have to figure out what these values are. Alpha 1, we have to use the right-hand rule to think about the sign of this component. Put your hand in the direction of alpha 1, your thumb's coming out. The z-axis, if x is this way and y is this way, would have to be out because of the right-hand rule. Anyone have any questions about that? Okay, so this is going to be 0, 0, 5. Right-hand rule says the same thing about omega 1. That has to be 0, 0, 10. Now, what's the definition of R? R is the vector that goes from the center of the circular motion to the point that you care about. Well, if you let this thing move in a full circle, the center of that circular motion would be the pin, the point that doesn't move. So the R vector goes from the pin to A. Okay, you with me on that? Okay, so that's going to be what? Use cosine and sine, that's going to, and times the length of 1. So that's going to be 0, you stupid idiot. Okay, that's going to be, you can think of that as cosine and sine of negative 30 degrees. So that's going to be 0.866, negative 0.50. And so all together, we get an answer for the acceleration of that elbow point A of negative 84.1, 54.330. Is that what you got too?
Yeah.
Yay. Well, that's the order of the arguments then. Okay, well, we're not done yet. That's just the acceleration of that elbow point. Okay, so now we have to do, and we don't have time to do it, but I'll set it up. So now the acceleration of P relative to the elbow point, you can think of it as assuming that that elbow point is not moving, okay, is equal to, we're going to use the watermelon equation again. This time alpha is positive and omega is negative. I should say 2. Okay, so we have 0, 0, 20 crossed with the vector from the center of that circular motion, A, to the point we care about. So that's just going to be 1, 0, 0. Plus 0, 0, negative 8 crossed with 0, 0, negative 8 cross 1, 0, 0. And then once we calculate that, we're going to say the acceleration of P relative to G is equal to the acceleration of P relative to A plus the acceleration of A relative to G. Any questions about the flow of this? We're going to spend more time on this. Yes?
That last equation, that's like the antithesis. That's, you know, your vector triangle.
Yeah, except now it's acceleration, so it's not as easy to visualize, but yes. Yeah, it all comes from that vector triangle, yeah. And so, I mean, this is cool, right? Like, would you have had any idea? Maybe you did this in Physics 1, but I think most of you probably, you'd look at that and be like, it's absolute chaos. You have no idea what to do. But with relative motion and circular motion, you just put these two things together and you can calculate how that endpoint is accelerating or what the velocity of that endpoint is, just using the velocity things instead. Yes?
Whenever you ask for like an acceleration of a point, you want it for it relative to a fixed point origin.
That's right, yeah. I'll try to be clear about that, but yeah, if I ever don't give a point, you can assume that it's relative to the ground.
Okay.
Yeah. Okay, that's all. So Monday, we'll just go through some examples. I'll have you go through some examples as groups, and we'll just get used to this stuff. And I'm going to give you some problems like this, but if you can't figure out how to get through it, that's okay. We'll go through stuff in class, and then you don't turn it in till later that night or whatever anyways.
Scroll through the types program watermelon. You have the,
This one? Yeah.